Dear students, continuing with our lecture series on named reactions, this is our 32nd lecture in this series, and today we will discuss about the chemistry and applications of benzoin condensation. Benzoin condensation basically is condensation of aryl aldehydes to give us benzoins as the product. And the most commonly used catalyst in the earlier times when benzoin condensation was explored was potassium cyanide or sodium cyanide. Basically, cyanide ion act as a nucleophile in these types of conversions where aryl aldehydes they are converted into benzoids. But as you know, these cyanide salts they are very toxic in nature. So with the passage of time, the use of cyanide was prohibited, and these catalysts now have been replaced by different types of other catalysts which have been found effective for benzoin condensation. And one of the common catalyst which is being used these days is thiazolium salt. And this thiazolium salt is also effective for benzoin condensation, but uh, in many reactions with one of this reaction is stator reaction. This also act as a catalyst where instead of benzoin condensation, the carbonyl compounds they react with alpha beta unsaturated ketones or the derivatives to give us 1,4 addition products. And formation of 1,4 addition products is called as stator reaction, whereas a reversible formation of 1,2 addition products is known as benzoin condensation. So depending upon the substrates, when we use thiazolium salts, either we will get benzoin condensation products or we will get stator reaction products. And we will in this lecture we will discuss about benzoin condensation, but the difference between benzoin condensation and stator condensation will be clarified in the next lecture, which will be on stator reaction. Now, as far as mechanism of the benzoin condensation is concerned, this was given in 1903 by Lapworth, and according to him, the benzoin condensation is a reversible reaction. So, a reversible reaction means the formation of products is controlled by the thermodynamics of the reaction. So, relative thermodynamic stability of the products in comparison to the reactants will determine that how much of the product in case of benzoin condensation will be formed. So here what happens is, in the first step, the cyanide ion acts as a nucleophile and attacks this electrophilic carbon which is attached to a double bond with this oxygen, and this leads to the formation of these types of intermediates. So cyanohydrins, they are formed as intermediates when cyanide ion reacts with the aryl halide. Then these cyanohydrins they undergo removal of this uh, proton which is present at the alpha carbon to this electron withdrawing cyano group to give us these types of negatively charged intermediates where negative charge is present on the nitrogen, and this can delocalize to give us back the cyanide ion, and this carbon will attack as a nucleophilic carbon to the electrophilic carbon of the second molecule of the aryl halide, and these types of anionic cyanohydrates, they are formed as intermediates. And then shifting of the proton from here, it will take a proton from water, and we will get these types of intermediates which will undergo removal of water from here, and cyanide ion which was added in the first step, because it is acting as a catalyst, it is removed in the last step, and we will get benzoin products in this way. And you can see all the steps in this reaction, they are reversible steps. So benzoin condensation is a reversible condensation where the product formation will be determined by the thermodynamic stability of the products. Then, as I have told you, that because of the toxic nature of cyanide ions, these have been replaced by many other type of salts which act as catalysts. So, a clue was taken from bioorganic chemistry, where thiamine acts as a coenzyme which is used for the biosynthesis of acetylene type compounds through benzoin addition reactions. So based on this, thiazolium moiety was thought to be a better catalyst for these types of benzoin condensation reaction. And when this was tried, it was found so also that even asymmetric benzoin condensation was achieved when we used chiral thiazolium salts as catalyst. And later on, these chiral thiazolium ions, they led to the development of Triazolium salts as catalyst, and it was found that in case of asymmetric benzoin condensation, even these triazolium salts, they are better than the chiral thiazolium salts. So these triazolium salts, they gave greater enantiomeric access in case of benzoin condensation products in comparison to thiazolium salts. So for example, in this type of intramolecular benzoin condensation, where here we are having aryl aldehyde group, and here we are having an aliphatic ketone group. So when this was reacted under basic condition in presence of potassium tertiary butoxide as a base, in presence of this chiral triazolium catalyst, then we got asymmetric benzoin products in with high enantiomeric excess of the order of 98% enantiomeric excess, and products, they were also formed in high yield, that is of the order of 91% this particular case. Then another type of catalyst which was also found effective for benzoin reactions was N-heterocyclic carbenes. And these N-heterocyclic carbenes, they followed a slightly different mechanism than the normal benzoin condensation mechanism which we have seen with the cyanide ions or thiazolium ions. Here, this mechanism is called as Breslow mechanism, based on the name of the scientist who gave this mechanism. And these N-heterocyclic carbene catalyzed reactions, they are generally explored for the coupling of catalytically generated acyl anions in case of wide variety of aldehydes, ketones, and even carbon nitrogen double bonded compounds like amines also. And recently, even synthesis of heterocyclic compounds has also been achieved using these types of N-heterocyclic carbenes as the catalyst. So basically what happens is this N-heterocyclic carbenes, they are resonance stabilized in presence of base into these types of salts. And these NHCs, they react in the first step with the carbonyl compounds, that is aryl aldehydes, and addition of one to addition of the carbines will take place to these uh, electrophilic carbon, and this type of anion is formed which will abstract a proton from water, and we will get these types of alcoholic intermediates. Then the alpha proton from these alcohols is eliminated to convert these into enols, and these enols, they act as nucleophiles to add to the second molecule of the aryl halide to give us these types of intermediates which undergo 1,3 hydrogen shift from here to here. So this H is transferred from this oxygen to this oxygen, which is called as 1,3 hydrogen shift. 1, 2, 3. 1, 3 hydrogen shift take place, and we will get these types of anions which undergo elimination of the NHC or the catalyst which we have added in the first step, and we will get ultimately benzoin products in this case. And this whole mechanism is called as Breslow's mechanism for synthesis of benzoin condensation products. Then some important examples of these benzoin condensation. In case of asymmetric benzoin condensation, these are catalyzed by n-heterocyclic carbines, where intramolecular cross-benzoin reaction will take place between this aryl aldehyde group and this ketone group, and these will undergo benzoin condensation in presence of these types of camphor derived triazolium pre-catalysts which are chiral in nature, and in presence of dbu as the base, we will get the anisotselective products, where the anisotselectivity of the product formed is very high, of the order of 93%, and yield of the product formed is also extensively high, that is up to 99% yields of the products can be formed. So these types of chrominones, they are formed from intramolecular cross-benzoin reaction of these types of carbonyl compounds. Similarly, we can synthesize these types of dihydroquinolinone derivatives with high enantiomeric access and high yield using this same type of Triazolium catalyst, and here the base is used as sodium acetate instead of DBU, and here this instead of this ether moiety we are having monomer, and that is why we are getting these dihydroquinolinone derivatives from these types of antethered ketoaldehydes as the substrates. Similarly, we can also get cross benzoin condensation products when we react aliphatic aldehydes with aromatic aldehydes, or aromatic ketones, or aromatic ketoesters. So in this particular case, when aliphatic aldehydes, they are reacted with alpha ketoesters, so this is ester moiety which is having a alpha keto group. So alpha ketoesters, when they are reacted with aliphatic aldehydes in the presence of triazolium catalysts of this type in presence of the base, then we will get highly chemoselective and anisotselective benzoin products. So anisotselective, when one of the ionomer is formed in much more amount in comparison to other ionomer, and chemoselective means out of these two, only one will act as lactophile and other will act as nucleophile. So depending upon these, we will get highly chemoselective and anisotrophic product in these types of cross-benzoin reactions. Then some more modified triazolium catalysts of these types, they have been used for different types of benzoin condensation reactions. For example, in case of benzoin condensation of aryl aldehyde, these types of bifunctional protic pentafluorophenyl substituted triazolium precatalysts, they have been used for anisotrophic synthesis of benzoin condensation products. Similarly, the aliphatic aldehydes, they can undergo cross benzoin condensation reaction with aryl halides in presence of these types of fused ring triazolium salts as the catalyst. So here also we will get products through n-heterocyclic carbene catalyzed reactions. So these are the references which have been consulted for preparing this lecture. Thank you very much.